basically the join of these two relations is guaranteed to give us back what we had originally. Now, the remaining two lines of the algorithm compute after the decomposition the set of functional dependencies for the decomposed relations and then the keys for those. I'm going to come back to this particular line here after doing an example. This is our same example, although squished to give me more space to write. And as a reminder, in this example, we've computed a couple of times that the key, given the functional dependencies, is the combination of the Social Security number and the high school code. So our goal is to take the student relation and iteratively break it down into smaller relations until all of the relations are in Boyce-Codd normal form. So let's start the iterative process. We pick some functional dependency that violates Boyce-Codd normal form, and we use it to guide our decomposition. So all three of these functional dependencies actually violate Boyce-Codd normal form because none of them have a key on the left-hand side. So let's start with the high school code one. So to do the decomposition based on this violating functional dependency, we're going to create two relations. The first one is going to contain just the three attributes that are in the functional dependency itself. So it's high school code, high school name, and high school city. And the second one is going to have all remaining attributes in the relation plus the left-hand side. So we'll have the Social Security number, the name, the address. We will have the high school code because it's on the left-hand side of the functional dependency we're using, but we won't have the name and city from the right-hand side, and we'll have the GPA and the priority. Now at this point our algorithm computes the functional dependencies for the decomposed relations. For this particular example we can just see what they are. They're the same functional dependencies that we had for the non-decomposed relation. Sometimes there's a little bit of computation you have to do, and I'm going to talk about that in a bit. But in this case we can see, for example, for our relation S1, the only functional dependency is this functional dependency here. That tells us that high school code here is a key for S1, so our only functional dependency has a key on the left-hand side, and that tells us that this relation is in Boyce-Codd normal form. So we're done with that one, but we're not done with S2. So for S2, the key is still the Social Security number and high school code together. So we still have these two functional dependencies that are Boyce-Codd normal form violations. So let's take the GPA priority one and let's guide that to decompose S2 further. We'll decompose S2 into S3 and S4. S3 will contain the GPA and priority from the functional dependency we're using. And then S4 will take the remaining attributes in S2 together with the left-hand side, the GPA. So we'll keep our Social Security number, name, address, high school code, and GPA, but we don't keep the priority. So at this point, S2 is completely gone. And let's take a look at the remaining relations. S3 now just has one functional dependency that applies, and the left-hand side is now a key. And so now we're done with S2. It's in Boyce-Codd normal form, but we're not done, we're done with S3, but we're not done yet with S4. S4 still has Social Security number and high school code as its key, and so we still have a violating functional dependency, so let's decompose S4 further. We decompose into S5 and S6. S5 contains the attributes in the functional dependency that we're using now, so it's the Social Security number, name, address, and GPA. And then S6 contains the remaining attributes plus the left-hand side, so that's the Social Security number and the high school code. And I will just tell you right now, because you might be getting bored with this example, we're done with S4. S5 and S6 are now both in Boyce-Codd normal form. So this is our final schema. It contains four relations, S1 with the information about high schools, S3 with the information about GPAs and priorities, S5 a student with their name, address, and GPA, and S6 a student with the high school they went to. And if you think about it, this really is a good schema design, and it's what's produced automatically by the Bcnf decomposition algorithm using our functional dependencies. Let me mention a few more things about the algorithm. First of all, I left this step kind of mysterious, which is how we compute the functional dependencies for the decomposed relations. We can't just take the functional dependencies we already have for the bigger relation and throw away the ones that don't apply exclusively to one or the other of the decomposed. We actually have to compute the functional dependencies that are implied and that apply to these relations. So in the video on functional dependencies, we learned all about implied functional dependencies, and we would use the closure as we did in in that video to determine the implied functional dependencies. Now, the reality is for many examples, it's pretty obvious. We saw in the previous example it is. And the other thing is that this is being done by a computer, so we don't actually have to worry about it except when we're doing exercises for our class. Second, let me mention that there's a little bit of non-determinism in this algorithm. It says pick any of our relations with a violating functional dependency and use that to guide the next decomposition step. So the fact is that you can get a different answer depending on which one you choose at this point in time. All of the results will be Bcnf decompositions, but they might not be the same one. And in fact, if you go back to the example that I did and you pick the functional dependencies in a different order, you might get a different final schema. But again, it will be in Bcnf. And lastly, some presentations of the Bcnf decomposition algorithm actually have another step here, which is to extend the functional dependency that's used for the decomposition. So we're using A to B, but if we have A to B, we also have A to B, and we can add more attributes, those in the closure of A, if you remember the closure, and that's also a correct functional dependency. By doing this extension, we will still get a correct Bcnf answer, but we'll tend to get relations that are larger than the ones we get if we don't do the extension first. In some cases, larger relations are better because you don't need to join them back when you're doing queries, but that can depend on the query load on the database. So to conclude, does Bcnf guarantee a good decomposition? Well, of course the answer is yes, or I wouldn't have spent all this time teaching you about it. Does it remove the anomalies that we looked at in our first example in another video of bad relational design? Yes, it does remove anomalies. When we have multiple instances of the same piece of information being captured, that's what's squeezed out by the decomposition into Bcnf. And that's fairly easy to see through the examples that we've done already. It's a little less obvious seeing why Bcnf composition does allow us to have a breakdown of a relation that logically reconstructs the original relation. So let's look at that a little bit more. So we're taking a relation R, we're producing R1 and R2, and we want to guarantee that when we join R1 and R2, we get R back. We don't get too few tuples and we don't get too many tuples. So too few is pretty easy to see. If we break R into R1 and R2 and they're projections of R, then when we join them back, certainly all the data is still present. It's the too many tuples that's a little bit more complicated to see, and let's just use a simple abstract example. So here's a relation R with 3 attributes, and let's have 2 tuples, 1, 2, 3, and 4, 2, 5. And let's suppose that we decompose R into R1 and R2. R1 is going to contain AB, and R2 is going to contain BC. So let's fill in the data. In R1 we have 1, 2, 4, 2, and in R2 we have 2, 3, 2, 5. Now let's see what happens when we join R1 and R2 back together. When we do that, you might see what's going to happen. We're actually going to get 4 tuples. We're going to get 1, 2, 3, 1, 2, 5, 4, 2, 3, and 4, 2, 5. And that is not the same as our original relation. So what happened? Well, what happened is we didn't decompose based on a functional dependency. The only way we would decompose with B as the shared attribute were if we had a functional dependency from B to A or B to C. And we don't. In both cases, there's 2 values of B that are the same, where here the A values are not the same, and here the C values are not the same. So neither of these functional dependencies hold, and Bcnf would not perform this decomposition. So in fact, Bcnf only performs decompositions when we will get the property that they're joined back. Again, that's called a lossless join. So Bcnf seems great. We just list all our attributes, a few functional dependencies, and the system churns on it, and out comes a wonderful schema. And in general, that actually is what happens. In our student example, that worked very well. There are, however, some shortcomings of Bcnf, and we will discuss those in a later video.